Okay, so yesterday we were playing with exponential functions and rates of change. So looking back at the most basic one, y equals e raised to the x. We've been looking at things with e to the kx, right? And I called k the exponential growth rate. Now that's not the same as like an annual growth rate. Like remember we talked about the annual growth rate for inflation was about 2%. Okay, and we then compared e to the kx as the base to 1.02 to the x. Okay, and they both, that x is the same thing in both of those, so I can essentially pull that out and just compare the bases. The bases then become e to the k and 1.02, right? And then to solve for k, what do? Natural log, so then k is equal to the natural log of 1.02. Okay, what's the natural log of 1.02? Anybody with a calculator handy?
1.02.
Natural log of 1.02, yep, to
0.0198026.
0.0198, blah, blah, blah. Okay, so if I rounded that to like 2 decimal places, what would it be? 0.02.
Whoa.
So it's approximately the growth rate. Okay, is it exactly the growth rate? No, right? So in this case, we have an APR, annual percentage rate, of 2%. And that's approximately equal to the exponential growth rates. Right there. Now, that approximation only works relatively well for small growth rates. The bigger the growth rate, the more of a problem that is. So what I'm going to do to enhance that comparison is just consider that this is 1 plus r, right? And I'm trying to find an associated value of r up there. So k is kind of a rate also. All right, so check this out. That means I'm essentially comparing the function e to the x to the function 1 plus x. And what do you notice about e to the x and 1 plus x? Not only do they meet,
they have the same slope.
They have the same slope. Yeah, what's e to the power 0? 1. So that means the slope of e to the x at 0 is 1. And the slope of my line is 1. Yeah, so it turns out 1 plus x is the tangent to e to the x on the y-axis at that y-intercept. Okay. And what happens if you zoom in on where a function and a tangent line meet? They're pretty tight, right? They're buds. They match. So that's my point. As long as the x is small, in this case, x is my growth rate, then e to the x and 1 plus x are pretty darn close to each other. So an exponential growth rate will be approximately equal to the regular growth rate for small growth rates. What if the growth rate was like 60%? Are they close there? Right, 60% would be right here, right? So here they're a little farther apart, right? So that's going to be a little too far out there. But for things like 1%, 2%, they're pretty tight, okay? Not too far off. We can use them to approximate each other. So oftentimes in problems like these, people will just use, if it's a small growth rate, they'll just use that as the exponential growth rate also, because they're close. All right. Next thing I wanted to mention about exponential growth was the idea of compound interest. So I talked about simple interest last time and exponential growth rates, but way back in your math career, you probably looked at compound interest. It usually comes up in an application of pre-calculus or college algebra. And the formula, the future value of some present amount, is times parentheses 1 plus, I'm going to say r is my APR, divided by n, the number of times I collect interest each year, raised to the power nt. And I'll define all of these. This is in the book too, here to read it. So future value is what I'm calculating. I have to start off with some balance or present value. also called the principal sometimes. R in this case is an annual percentage rate. Often called an APR. N is the number of periods per year you collect interest. And you could consider it like a delta X. It's the amount of time, how many pieces we chop up a year into. And then T would be time in years. And I talked about the other day that whenever you're playing with percent change, you got to make sure that the rate the percent covers matches the time you're using. So if we have an annual percentage rate, we got to measure time in years. If we have a monthly percentage rate, we have to do time in months. If we have an hourly rate of change, we have to do time in hours, and so on. Okay, so the question, interesting question arises here. Well, wouldn't I be better off getting interest every month instead of interest just once a year? Okay, so let's check it out for the same interest rate. So let's assume like our P is $100, and let's let our interest rate be 12%. We get a killer deal, right? Good luck finding that anywhere. And then let's let n equal 12, which means you're collecting interest monthly. And so I want to know what happens in 1 year. So those are all the variables. So then my future value would be 100 times 1 plus 12% as a decimal divided by 12 times a year. And then I'm only going for 1 year, which means my exponent is 12 times 1, or just 12. All right, what about a calculator? What do you get?
Well, 112 and 68 cents.
68 cents.
Or 112
Cool.
68 cents.
$12.68.
So I got an extra 68 cents. If I only collected interest at the end of the year,
And you got an
I would get-
$12.
It's $12.
$12.
I get an extra $12?
$112.
It's 112.68.
okay. So if I only collected interest at the end of the year, how much interest will I get? What's 12% of 100? $12. Yeah, I would only get $12. So am I better off getting it monthly than just once at the end of the year? Yeah, I'm 68 cents better. Something, right? If I made a bigger investment, like $1 million, it would be more than 68 cents, right? Okay. So what about collecting interest every day? Shouldn't that even be better than every month?
Yes.
Okay. So let me just make a note here. If I only collected interest once, so for 1 year, no compounding, then I would get a future value of exactly $112, right? 12% added on. If I collect interest every month, then I end up with $112 and about 68 cents. Well, to do it every day, I just switch out the 12 with a 365, right? Did you already calculate that?
Yeah.
Okay, so that would be 100, 1 plus 12% over 365 to the power of 365, which gives me about
$112.75 or 74 because they round down.
74 cents. All right, so I did what, 6 cents better than, oh man, only 6 cents better. So like, what if I collected interest like every second of the day for a year? All right, let's see what that would look like. So let's see, there are 365 days in a year, right? In a day, there are 24 hours. In an hour, there are 60 minutes. And in a minute, there are 60 seconds. So therefore, there are, let's see, what does that give me? 1, 2, 3, 31,536,000 seconds in a year.
It gives it in like scientific notation.
Okay.
So
then if I type that as my compounding period, it's just going to be 100 times parentheses, 1 plus 12%, 0.12,
You want to
divided
see
by
this?
that number. I'm going to call it B. Oops. That.
You want to see that?
Oh, you can't see what I'm doing. Shit, thank you. I mean, shoot, sorry. All right, so divided by B raised to what power? B. And I get, oh,
75 cents. Or no, still
we
74.
got up to 75 cents, almost,
It would, yeah.
The
it's
other
every
one-
second. So although I'm getting interest way more often, the problem is I'm getting less interest at each period, right? Because I divide the interest rate by that number, but then I raise it to a bigger power. So although I'm getting more and more money, the amount more is decreasing. This is what's called diminishing marginal returns. Okay?
Technically, you get
The
same-
rate of increase of my return is decreasing
Exponential.
in a kind of asymptotic way. So I'm going to show you a graph of what this looks like. What we're playing with, our variable here is that B. Okay, so I'm gonna oversimplify this problem.
Is it
So
ever
let's-
going to hit 75?
Banks
What's it
round-
gonna hit? That's the
Do
question here.
banks round?
Okay.
They're like near center.
The bank has the option of rounding or chopping,
That's what.
so they could call it 74 cents.
So the other
technically.
one's 74 too.
Yeah.
When they want it,
The other thing is they can also say there's only 360 days in a year, because on average there's 30 days in a month. 30 times 12 is 360.
Seriously?
Yes, and legally, actually, they can use any whole number between 360 and 365
Oh wow.
if they wanted to. Yeah, there's some weird laws about that.
It's in the fine print.
All right, okay, so check this out. So I'm just going to isolate this rate of change that's going on. The only thing changing is my compounding period, really. Okay, so that means my function can simplify as follows: 1 plus 1 over x to the power x.
so they add some toast.
Come here. Oh, am I not? I want you shift. Hello.
Oh,
There we go. Yeah. So if I redraw this picture a little bit, there is a horizontal asymptote. Okay. Now this would be collecting interest 100 times a year. Were we getting interest way more than that? Yeah, 31 million times a year. We were getting interest, right? So notice this flattens out pretty quick. All right. So pretty flat. Do I care about the negative side? No, right? Because this is x is number of times a year. So what is f of 10,000? 2.7181. Man, I've seen that number somewhere before. E, holy crap, it's E. Yeah, so this is the cool thing. If you take this compound interest formula right here, and you take the limit as n goes to infinity, which is kind of what I was aiming at in that graph, the base becomes E. So what happens is, I'm not going to do all the algebra for it. If I take the limit as n goes to infinity of 1 plus r over n to the power n, if we let time come out of this for a minute, just assume it's 1 year, then this turns into e to the r. Okay. And the other formula is called the compound interest formula. This is called
Continuous.
continuous compound interest. Thank you. There we
Did a
go.
problem about that.
Yeah.
I had to look it up.
So this when n goes to infinity, this gives us continuous compounding. We're always compounding. We're never not compounding, right? So it's better than every second. It's better than every billionth of a second. It's always collecting interest, never not. That's called continuous compounding. Really freaky idea. Continuous compound interest. So because of that limit above, the future value formula just turns into P times E to the RT.
Correct.
Which, doesn't that look like just like the exponential growth rate formula we were using yesterday? That's just the same thing.
Me too. It was almost all on his heads.
Okay.
I mean,
So there's a couple of problems that ask about continuous compound interest versus like getting interest every day or every minute. Okay, those are the last two problems I wanted to do in section 8. Next, hyperbolic trigonometric functions, section 2.9. Okay, so I'm just going to show you a picture of why they're called hyperbolic trig functions, and then we'll do some algebra with them, and then a little bit of calculus. Hyperbolic.
Are we doing this tomorrow in class, or are we reviewing for the test?
Tomorrow we're reviewing for the test. I'm going to finish this today. Okay, so hyperbolic trig functions care of Wikipedia. All right, let's open that in a new tab. There we go. So they show the graphs of 3 different functions. My favorite is what's called the cosh, the hyperbolic cosine. That is that green U-looking shape. It kind of looks like a parabola, but it ain't a parabola. Its graph has a special name. I talked about it in class before. It starts with a C. Catenary, or catenary, depending on how you choose to pronounce it. Yeah, and a catenary is the physical shape that a cable makes, or a chain, when you try to string it between 2 points. Or a string. Anything of relatively uniform density that gravity is going to pull down on, it forms that shape between the 2 points. Okay? And there's a whole physics proof of that, which I am not capable of doing today. So we're just going to go with it. So then we have these other cute functions, like this funky red function that looks kind of like x cubed, which is interesting because the cosh looks like x squared. And then there's the hyperbolic tangent, which is that cute little dotted blue line there. So why are they similar to regular trig functions? So that gets to this picture down here. So new tab. So this black function right here is called a hyperbola. You remember studying hyperbolas maybe in some class before? Okay, they're kind of like parabolas, but they have asymptotes. So for example, x squared minus y squared equals 1 has 2 slant asymptotes. One is the line y equals negative x, the other is the line y equals positive x. Okay, and then this curve tries to touch each of those asymptotes in each direction. And that idea, that's called a hyperbola. If you then pick a point on the hyperbola, like, ooh, whoa, I didn't know that happened.
You're not on.
Oh, I'm not in my
You're
screen.
not on draw, you're on Google still.
Can I undo that?
Control Z.
All right, there we go. All right, so if I pick this point on the curve right there, from that point I can make a ray down to the origin, and then I could find that area there, couldn't I? We know enough calculus to do that. Yeah, we could do that. If you double that area, so imagine that same region underneath a symmetric version of it. If you take the hyperbolic cosine of twice that area, that gives you the x value at this point. So there's a relationship between exponential functions, the area here, and the hyperbola x squared plus y squared equals 1. Now, can you think of another curve that's kind of like x squared minus y squared equals 1 that you played with before in a class right before calculus?
It's the
Trigonometry, x squared plus y squared equals 1 gives me the unit circle. And the unit circle leads to regular sine, cosine, and tangent. Well, it turns out the unit hyperbola leads to these hyperbolic trig functions. Why are they called hyperbolic? Because this is a hyperbola instead of a circle. Right? Hyperbola is related to circles. Yeah, look at that very similar equation. Right? They just throw a minus in instead of a plus. Okay? Is a minus a big difference? Oh yeah, sort of. But they're sibling functions, it turns out. Okay, so that's where the name hyperbolic comes from. So we have a function called the SINH, which is often read sinh, and sinh is the hyperbolic sine. And the definition of the hyperbolic sine is a fraction, e to the x minus e to the negative x in the numerator, divide by 2. That's the hyperbolic sine. There is also a hyperbolic cosine. That one's called cos h or cosh. And that one's very similar. It is e to the x plus e to the negative x over 2. And then they have lots of interesting properties. I'm only going to go over a couple of them, and I'll show you that Wikipedia page has almost all of them. Yeah, I'll do tangent now. Okay, I'll do tangent now. The hyperbolic tangent, or tanh, of x is just the hyperbolic cosine divided by the hyperbolic sine. I get that backwards. Hyperbolic sine divided by the hyperbolic cosine. Like tangent is sine over cosine. So the divide by 2's divide out, so you would get e to the x minus e to the negative x over e to the x plus e to the negative x. And it turns out there's another cute version of that. Like if you multiply top and bottom by e to the x, you would get e to the 2x minus 1 over e to the 2x plus 1. So there's a ton of interesting algebra you can do on these, but sometimes you'll see hyperbolic tangent expressed this way, sometimes you'll see it expressed this way, sometimes you'll see it expressed that way. It just kind of depends on what, sometimes one's more useful than the other. Some interesting identities. If you take the cosh and you add it to the sinh, you get e to the x. A whole bunch of stuff cancels. You could try that on your own and see. It's pretty simple to show. If you subtract them, any guesses?
Negative e to the negative x?
E to the negative x is what you would get if you subtract them. Yep. A bunch of stuff cancels. There's kind of a Pythagorean identity. It is the cosh squared minus the sinh squared gives you 1. Little different than our regular trig one, right? Our regular trig one says add the 2 of them together. This one ends up being subtracted.
It doesn't matter the order.
It does matter the order. Yes. If you change the order, you would get -1. So just remember with regular sine and cosine, right? It's the cosine of x squared plus the sine of x squared. Sine squared of x is 1. Why? Because sine and cosine come from the unit circle. The unit circle has the equation x squared plus y squared equals 1. Hyperbolic trig functions come from the unit hyperbola. And the unit hyperbola is x squared minus y squared equals 1. Hence the difference in the formulas. Okay. Amazing geometric significance to these things. And again, my most powerful reason for doing these with you is just that physics of hanging a wire or a cable. It's a hyperbolic cosine. It's pretty neat. Turns out they have some awesome integration benefits that we're going to get to. All right, so here's, oh, this is another amazing fact about these things. Check this out. This just blew my mind the first time I saw it. So consider finding the area under part of a hyperbolic cosine. So that means I would integrate from some number a to some number b of the cosh of x dx, right? So now I'm going to perform a little algebra jiggery-pokery here, a little algebraic magic, based on the Pythagorean identity for hyperbolic sine and cosine. Okay? So if you consider that formula I had a minute ago, it's the cosh squared minus the sinh squared. That means if you isolated the hyperbolic cosine, then it's the, you could say it's 1 plus the sinh squared. I'm going to leave the squares in there. Oh, yeah, I guess, yeah, let's do the square root. What the heck, why not? So like Daphne said, if we take the square root of both sides, then we get this hyperbolic cosine equals the square root of 1 plus the square of the hyperbolic sine. Cool, I just created the substitution, right? How would I do that? That looks worse, but wait, this is so cool. So now I have the integral from a to b of 1 plus the sinh squared. I'm going to write it a little bit different, inside of the square root. So that's what that identity gives me. Oops, my 1 is kind of hiding there. Sorry about that. Switch it over. Okay. Now, even better. Guess what the derivative of the cosh is?
Negative sinh.
Turns out it's just the sinh. And the derivative of the sinh is just the cosh.
Wait, so it doesn't
Okay.
have a negative
Okay.
positive thing?
So side, let's go back. No, it turns out it doesn't.
So it just goes sinh cos.
Yeah. So again, the cosh of x is e to the x minus e to the negative x over 2, right? Take the derivative of that.
E to the x plus.
Yeah, so when I take the derivative of this right there, well, the over 2 is just a constant multiple. It just chills out.
Changes.
E to the x is e to the x, but then I'm going to get a minus e to the negative x, cancels that minus, so now I get plus e to the minus x, which is the definition of the sinh. It's just the straight sinh. Yeah, and if you go the other way, you get just the straight cosh. So it turns out the derivative of the cosh is the sinh, and conversely, the derivative of the sinh is the cosh.
And then the antiderivative is just.
Yeah, and then the antiderivative of the sinh is cosh, and the antiderivative of the cosh is sinh, right? We get all these beautiful relationships. But you haven't seen the best part. Wait till you see this.
The tangent.
A tangent's something else. We'll do a tangent, whatever. Okay, you ready?
No.
No.
Okay, I'm gonna do it anyway. So, this guy right here happens to be the derivative of the cosh. Okay, so check this out. So this, now I have the integral from a to b of the square root of 1 plus the derivative with respect to x of the cosh of x squared inside there. And wait, that formula looks like
Oh, the arc length.
arc length. Oh my gosh. The area under the cosh has the same value as its arc length. Because that's the arc length formula. Right? The arc length formula is 1 plus the derivative of the function squared inside the square root.
Oh shit.
Right? If this sucker right here is f of x, that right there is f prime of x, which is the calculus version of the Pythagorean theorem. Oh my gosh, isn't that crazy?
Here, I missed something in my notes.
Yeah.
Is sinh e to the x minus e to the negative x?
Yes, and cosh is e to the x plus
Okay,
e to the negative x.
okay.
So
Yeah, so it turns out
The area and the arc length.
the area and the arc length have the same value. Now, they don't mean the same thing, right? Area is square units and length is linear units, but their integrals spit out the same numbers, which is like, whoa, craziness.
See me.
Wait. How would that work?
Yeah.
So does it have no?
Wait. Okay, like apply that
Okay,
to like a real
so-
thing.
Show
Alright.
me a shape.
Yeah, and then like,
Okay.
like that's that.
All right, so GeoGebra. Let's do some physical math here. You don't save. All right, so let's just take a look at the graph of the cosh. Can GeoGebra do the cosh? Yes, it can. Rock GeoGebra. Okay, so there's the cosh there. Okay, it is not a parabola. If you try to make a parabola sit on top of it, it's not going to sit on top of it perfectly ever. It's not possible. It's a different function. Okay, what function is it really? Well, remember, it is the quotient of e raised to the x plus e raised to the negative x. Okay, so let's make that red for fun. Settings, color, red, right? They're the same function. Because the definition of the cosh is that. All right, so next thing I'm going to do is I'm going to find the area, let's say the area under the curve from -1 to 1. Okay, so I'll do it two different ways. One way is I start typing int, and GeoGebra says, hey, you want a numerical integral? I say, sure. Use the function f, start at -1 and go to 1, and then GeoGebra shades in the area I just found. The value is about 2.35-ish. Okay, what's our formula for arc length? Reminder, arc length of a function is the integral from a to b of the square root of 1 plus the square of the derivative. Okay. Okay. So let's type that into GeoGebra. So what do I want to do here? I want to set up another integral. My function this time is a little more complicated. It's the square root of 1 plus, what's the derivative of the hyperbolic cosine? Hyperbolic sine, so I type in SINH, and GeoGebra says, I know that function of x. And then I have to square it. So I needed an extra set of parentheses to square it. No, I'm in the right spot. I'm squaring the sine. I put parentheses around the sine there.
Oh, okay, cool.
And I'm squaring that. Okay, so that's my integrand, true? Okay. And then I want to integrate that from -1 to 1. And I got 2.35042387. It looks like the number above. So they're the same number, but they have different meaning. The first number is the square units up here. So like maybe those are square centimeters. But it turns out the distance, if you travel on this curve from that point to that point, happens to be the same number, but centimeters.
So like
Okay.
on a test.
So the area is 2.35 centimeters squared. The length is 2.5 centimeters. What's up?
It's like on a test, if it said find the arc length of the cosh, we could just find the integral from those values.
Okay, so check that out. Yeah, so suppose the question was find the arc length. Arc length of y equals the hyperbolic cosine of x from -1 to 1. Commas in there. Some eraser. Okay. Well, then to do that, I would need to say, hey, well, y prime is the hyperbolic sine of x. That means my arc is equal to the integral from -1 to 1 of the big old square root of 1 plus my derivative squared dx.
But we don't We could technically do it the other way, where we just take the integral of the function from those 2 points, and it would still give us the same number, and we could use that as like.
I'm getting there. Yeah.
Okay.
We have
So,
to show our work to-
I happen to know a trigonometric. What's that?
We have to show our work to.
You got to show some work, right? You got to. If I ask you to do arc length, you got to show me the arc length formula.
Okay.
However, we have an identity that says that is really equal to the cosh squared, and the square root of the cosh squared is the cosh, right? So by our identity, this becomes the integral from -1 to 1 of the cosh of x dx. Antiderivative for the cosh is just the sinh, so then I just have to evaluate the sinh from -1 to 1. Yeah, so it turns out, hey, wow, that cleaned up nice. And that's the key with any situation we're in. We try to do algebra before we do calculus. And there are a ton of identities. I'm not going to go over all of them. I'm just going to do a couple more. So if you, for example, if you open our book, the book's going to have like 4 tables of identity type stuff for hyperbolic sines and their inverses. If you scroll through the Wikipedia page, you're going to find lots of cute pictures, and then identity after identity after identity, all kinds of definitions. They have derivative stuff eventually.
I have Arc Sine.
Oh yeah, we're going to do arc sine next. Okay, good point. Okay, inverse hyperbolic functions. All right, so I'm not going to drive all of them because there are a lot of algebraic work. It would take hours. I'm just going to do one, and then we can just look up the others. So what I'm going to consider is f of x equals, let's see, I think I was playing with the sinh in my notes. Yeah. Equals the hyperbolic sine of x, which we call is e to the x minus e to the negative x over 2. Now I want to find the inverse function for that. So the procedure for finding an inverse function is you set it equal to y, solve for x, and then switch the variables. Or vice versa, switch the variables and solve for y. So I'm going to rewrite this as y equals, actually I don't want that anymore. I'm going to use the exponential version because that's useful here. Y equals e to the x minus e to the negative x over 2. All right, so I'm going to solve for x and then switch the variables. All right, I guess I'm going to multiply the 2 to the other side. So 2y equals e to the x minus e to the negative x. Now here I have a problem in that there's x's in 2 different places, and I can't, in order to solve for x, I need to get down to a single x. Okay. So I'm going to do a little substitution here. I'm going to let u equal e to the x. Well, guess what e to the negative x would then be? No derivatives here. What does negative exponent mean? It means flip it. So that must be 1 over u. Okay. So with that substitution, I now have 2y equals u minus 1 over u. Now that u in the denominator is a bit of a problem, right? So I'm going to multiply both sides by u. So that's going to give me 2yu equals u squared minus 1. U squared. Quadratic formula might help. Quadratic formula, you get everything on one side. So I'm going to subtract that 2yu to the right side. That's going to give me 0 equals u squared minus 2yu minus 1. Now I can use the quadratic formula to solve for u. Once I do that, I can then solve for x. Okay, quadratic formula. So I currently have u squared minus 2yu minus 1 equals 0. So quadratic formula, a is 1, b is negative 2y, and c is negative 1. Where u is the variable I'm solving for. Quadratic formula says u equals the opposite of b. So that would be just 2y. Plus or minus the square root of b squared. Let's see, that would be 4y squared. Minus 4 times a is 1 times c is negative 1. All over 2a is just 2. Turns out this cleans up quite a bit, but not super. Inside here, that's going to end up being 4 is a factor times y squared plus 1. Right, because here I have minus and negative. So there's plus. They both have a common factor of 4, which I can pull out. And I like that because what's the square root of 4? 2. And so I have a 2 in the denominator, but now I have 2y plus or minus twice the square root of y squared plus 1 over 2. And guess what happens to those 2's?
They cancel.
They all divide out. Yeah, because I can factor 2 out of the bottom to cancel the 2 in the bottom. So now I have y plus or minus the square root of y squared plus 1. Now this is a bit of a problem because if it's a function, you can't have plus or minus because that's not a function. So the question is, well, which one do we want, the plus or the minus? Well, here's the answer. What is u really equal to?
E to the x.
E to the x. So it turns out e to the x is equal to that because that's what u is. Right, reverse substitute. E to the x can never be negative. Right? If you put a negative number in there, you get like 1 over e or 1 over e squared. It's still positive. So it can't possibly be negative. That's irrelevant. That's going to lead to imaginary numbers. So because e to the x has to be greater than 0, always, if you want to work with real numbers, that means that negative has to go away. Otherwise, we're stuck with complex numbers. How do we get x out of the power? ln, yeah. So it turns out, finally, that x is equal to the natural log of y plus the square root of y squared plus 1. And remember, finding an inverse function means to solve for x and then switch them. So now I get y, which is the inverse function, is the natural log of x plus the square root of x squared plus 1. And it turns out this function is what we call the inverse of the hyperbolic sine, which is referred to as the arc sinh of x. And that kind of makes sense, right? The regular sinh is an exponential function, so shouldn't its inverse be a logarithmic function? Because logs are the inverses of exponents. It's just kind of a wild one. All right, it gets better. Oh, we're out of time. Okay, so I got one more thing to do, which I'll have to do tomorrow. I'm going to show you what the derivative of the arc sinh is. I'll prove it tomorrow. So it turns out if you follow the chain rule, taking the derivative of that sucker up there, it cleans up quite nicely to that.
So it's exactly, well, no, is the plus different? Or as always? Because from
that's-
the regular arc sine,
Is it just?
because it's usually,
No,
but it's 1
negative on the
minus.
plot.
It's 1 minus.
So,
x squared.
yeah, so you're confusing this with the derivative of the arc sine. So the derivative with
that's-
respect to x of the arc sine,
And that's
the
1
regular
over
sine,
1 minus x squared, right?
I think it's negative. It's just negative.
1 minus x squared, yeah.
Is that, so before if we come up with an integral of 1 over 1 minus the x, I'm sorry, I'm excited, I'm losing my words. The integral of this is the arc sine. If that happened to be a plus, we were like, I can't do it. Now we can. Because the inverse, yeah. So what we're doing is now we're going to have a whole bunch more integration formulas for stuff we couldn't solve before, where we had to rely on like the integral calculator. Yay. So we're the inverse hyperbolic trig functions are going to open up a whole bunch of functions we can now find derivatives for and antiderivative for that we couldn't. That's the other reason we need this.
Lovely.
Yeah, fun stuff. All
I
right,
wasn't
so
expecting to learn more trig today.
tomorrow we'll do a couple more examples of this. Otherwise, tomorrow is a review day. I will post the take-home test tonight, probably, so you can get started on that. And I did make a post, and I messaged you guys saying the practice exam is up too. So check that out. Hello, Vitor.